Okay, so this is exam review for exam 3. This is the answer key. So number 1, starting off with the true and false questions. Electrons orbit the nucleus much like planets around the sun. I think most people got this one right, which it is false, right? It's definitely false. Remember we talked about how they're not orbits. They're orbitals instead. There's some probability distribution. There's some probability with which the electrons go around the nucleus, and they don't necessarily go around in circles or ellipses like planets do. They go in all sorts of different shapes, right? We have the p orbitals, the dumbbell shapes, the d orbitals, the clover leaves. Okay. Number 2, fluorium has 4 valence electrons, and so we're going to have to use the periodic table here. Fluorium is Fl right here, and so that one is going to be true because it's in the same group as carbon. So we would count over from lithium 1, 2, 3, 4 valence electrons. All molecules with polar bonds are polar molecules. Okay, this is false, and I talked a lot about this in the different lecture videos, and so you need polar bonds to have a polar molecule, but polar molecules aren't necessarily just have polar molecules need more than that. Okay, so for example, consider carbon dioxide. This is an example that we went over a lot in lecture. Carbon dioxide, if you draw the Lewis structure, looks like this. Okay, it's a linear molecule. You can put the lone pairs on the oxygen. That's fine. It's a linear molecule, and if you look up the electronegativity values, right, we know that oxygen is to the right of carbon, and so it's much more electronegative. Oxygen is one of these really electronegative elements. Nitrogen, oxygen, fluorine, chlorine, those are the 4 most electronegative elements, right? So this is definitely a polar bond, and so you're going to have electron density going towards the oxygen in the carbon-oxygen bond. In this case, this bond on the right, we're going to have electron density being pulled to the right. So the tug of war, oxygen is winning the tug of war, right? But there's also a tug of war going on, a polar covalent bond going to the left. And so those 2 dipoles that you've set up are in equal and opposite directions. And so your net dipole is going to be 0, right? And so what that means is that even though you have polar bonds, overall, this is a non-polar molecule, okay? So this is why this statement is false. There's certain cases, okay, and it's always true when you have no lone pairs on the central atom. Because when you have no lone pairs on the central atom, that's when your steric geometry and your molecular geometry are the same, and you have very symmetric shapes. So things like linear, things like trigonal, planar, tetrahedral. Okay, not things like seesaw or some of those the other shapes like T-shaped, right, where they're looking asymmetric. Those will likely you won't have the dipoles canceling out. Okay, so if carbon dioxide was bent, so consider a bent analog of this would be something like sulfur dioxide. Okay, sulfur dioxide. I'm not going through all the Lewis structure calculations, but I'm just telling you here. You can do it on your own time. Sulfur dioxide is bent, and again, these are polar covalent bonds. But here, right, it's because it's bent, because there's a lone pair on the central atom, the steric geometry isn't the same as the molecular geometry. Those 2 dipoles, one going a little bit to the right and down, the other one going a little bit to the left and down, are going to add up to give you a net dipole just going straight down. So that's a polar molecule that has polar bonds, but it's not necessarily true that all molecules with polar bonds are polar.